Here are some of the main points that I'm going to try to transmit today. Most problems in biomedicine and many problems in bioengineering boil down to the control of morphogenesis, the idea of controlling the collective decision-making among cells is critical for advances in many areas that are important for us. And I'm going to argue that this is not going to be solved by hardware-based approaches such as genomics and so on. In fact, biology uses a kind of multi-scale competency architecture of nested problem solvers in very different problem spaces. We, in evolution, exploit this architecture, and in particular, this bioelectrical interface that I'm going to tell you today that cells and tissues use to shape each other's behavior in the attempt to create and maintain complex functional structures. We now have tools that allow us to read and write memories into this software layer, this physiological layer of control that sits between the genome and the anatomy. And this has many applications in birth defects, regeneration, cancer, and also synthetic bioengineering. What I'm specifically going to emphasize today is engineering with agential materials, that is, materials with an agenda, where we can use tools from behavioral and cognitive sciences to exploit the intelligence and the competency of cells and groups of cells in these unusual problem spaces. So one of the key things that we have to do in order to start utilizing these amazing properties of the living material is to widen our ability to think about other problem spaces. So humans are pretty good at recognizing intelligence of medium-sized objects moving at medium speeds in three-dimensional space. So we see apes, we see some birds, maybe an octopus or a whale doing interesting things in three-dimensional space, and we can sort of understand this as intelligence. But there are all these other spaces. So there's the space of gene expression, there's the space of physiological states, and what we're going to talk about most of all, which is the space of anatomical states. And in all of these spaces, you can think about different types of systems at different time scales, at different in different embodiments, navigating those spaces adaptively. That is, making decisions, taking measurements, having memories, and trying to reach specific regions of those spaces. So let's talk about anatomical space. We'll have time today to mostly focus on that. So all of us begin life as a collection of blastomeres, but if you take a cross-section through a human torso, you see something like this incredible order. Everything is the right shape, the right size, the right orientation next to the right thing. Where does this incredible pattern come from? I mean, arranging this pattern in the space of all possible configurations is a very specific journey. So how do the cells know where they're going? Now, you might be tempted to say, well, it's in the genome, of course, it's in the DNA, and that's what most people would say. But the problem with that is that we can read genomes now. We know what's in the DNA, and it's nothing like this. What's directly in the DNA are protein sequences. So they are specifications of the nanoscale hardware that every cell gets to have. After that, the cells have to engage in a process we call developmental physiology, which allows them to build something like this. Now, that means we need to understand, how do cell groups know what to make and when to stop? How could we convince them to repair or rebuild if something is missing? And as engineers, we would also like to know, how much plasticity is there? Could we get them to build something completely different with the exact same genome, right? How reprogrammable is this hardware? What else is it willing to do? And the information on the final outcome is no more in the genes than the exact structure of the termite mound or the spider web is encoded in the genome of these animals. All of these things are outputs of behavior. This anatomy is no less an output of behavior than are these constructions. So where we are today in the biosciences is this: we're getting very good at manipulating cells and molecules. And so what do genes interact with what other genes and so on? We're really a long way away from large-scale control of form and function. If somebody needs their limb back after an injury, we really don't know how to make them grow back, or in fact, we really don't even know simple things like why do you have two bones in your forearm instead of one, despite all the molecular biology. So I think that what's happening here is that biomedicine has been stuck where computer science was in the 40s and 50s. So this is what it used to look like to program a computer. You'd have to physically rewire it. And the reason that today you don't have to get out your soldering iron every time you switch from PowerPoint to Microsoft Word is that we've understood the power of reprogrammable hardware, the power of using the information processing competencies of your material to control it with stimuli at a higher level, not just to rewiring. to rewire it. And biomedicine is, molecular medicine anyway, is largely focused on the hardware today. All the exciting advances are around genomic editing, protein engineering, pathway rewiring. It's all down at the level of the molecules. And I think the reason that we're still not close to being able to control what we actually want to control, which is form and function, is because we've barely started to take advantage of the higher level information processing or the intelligence and the decision making of the material.
Seem like I'm coming on strong, but I know just where it's at.